Welcome back, everybody. Today, we're going to be taking a deep dive
Oh, yeah.
into something that
Sounds pretty wild.
might blow your mind.
Yeah.
Don't we talk about magnetrons?
Magnetrons.
You know, that thing that powers your microwave?
Yeah.
And
I know, right?
the potential they might have to revolutionize particle physics.
What?
Yeah.
I know.
Wild.
Crazy.
Right. But that's what researchers over at the Thomas Jefferson National Accelerator Facility are exploring.
Yeah.
And we've got their research article right here.
It really is fascinating how something so commonplace could hold the key to such groundbreaking scientific advancements.
Exactly.
It's wild.
So let's start with the problem.
Okay.
Particle accelerators.
Right.
These massive machines that help us understand the universe at its tiniest level.
Yeah.
They're incredibly energy hungry
Oh, yeah.
and expensive to run.
Yeah, very much so.
And that limits their use. And it makes cutting-edge research pretty inaccessible.
Absolutely. That's been a major roadblock for research.
For a long time.
A long time.
Yeah.
Yeah.
So now enters the humble magnetron,
Yes.
which you probably know best for popping popcorn.
Yeah,
But
of course.
this little device is incredibly efficient.
Oh, yeah, definitely.
Over 70%
I mean,
of the energy it uses is converted into microwaves.
Yeah.
That's why your microwave doesn't send your electric bill skyrocketing.
And that's exactly what makes them so promising.
Yes.
For powering particle accelerators.
Exactly.
Imagine cutting the energy bill of a massive research facility by 70%.
Huge.
That's the kind of impact we're talking about.
That's wild.
Yeah.
But hold on. If magnetrons are so efficient,
Right.
why haven't we been using them all along?
Yeah. That's a good question.
There's got to be a catch.
Well, there is. The technology currently used in most high-performance accelerators relies on something called klystrons.
Klystrons.
They're another type of vacuum tube,
Okay.
but they offer more precise control over the particle beams.
So it's a trade-off
Yeah,
between efficiency
you got it.
and precision.
Exactly.
Yeah.
Think of klystrons as a high-performance sports car.
Okay.
Powerful and precise, but it guzzles gas.
Right.
Magnetrons, on the other hand, are like a reliable, fuel-efficient workhorse.
Okay.
They might not be as flashy,
Yeah.
but they can get the job done.
I'm starting to see the potential here.
Yeah.
But how did researchers even come up with this idea
Yeah.
of using magnetron for something as complex as particle acceleration?
Yeah.
It's not like they just stumbled upon it
Right.
while reheating leftovers.
No, not quite that simple. But
Okay.
there is a bit of a serendipity story here.
Okay.
It all started with radar technology
Okay.
during World War II. The magnetron was a key component in those early radar systems. And its ability to generate powerful microwaves caught the attention of scientists.
And then the microwave oven was born.
Exactly.
I remember reading about Percy Spencer,
Oh, yeah.
who was a physicist,
Right.
who accidentally discovered that a magnetron could melt a candy bar in his pocket.
That's the one.
That's a classic example of how
Yeah.
scientific breakthroughs can happen in the most unexpected ways.
Yeah, it's amazing.
Yeah.
But it wasn't until much later
Right.
that scientists started seriously considering magnetrons for particle acceleration.
So what sparked that interest?
Well, it was a combination of factors.
Okay.
The rising costs of running traditional accelerators,
Yeah.
advancements in magnetron technology,
Mm-hmm.
and a growing need for more compact and affordable particle accelerators.
Okay.
All played a role.
So it sounds like the stars aligned
Yeah.
and scientists at Jefferson Lab decided to take a chance.
Yeah.
On this unconventional approach.
Yeah.
So what's their main goal?
Well, their primary focus is on developing more cost-effective and energy-efficient particle accelerators.
Okay.
They're looking at ways to harness the power of magnetrons
Yeah.
to potentially replace those expensive klystrons we talked about.
Makes sense.
Yeah.
But I imagine there must be some pretty big challenges
Yeah.
in trying to adapt a technology designed for heating food
Right.
to accelerate particles
Yeah,
to near the speed of light.
definitely.
What are some of the hurdles they're facing?
Well, one of the biggest is stability.
Oh, yeah.
Magnetrons can be a bit finicky at different power levels,
Okay.
and they have issues with frequency changes and noise,
Oh, I see.
which can really mess things up when you're dealing with particles moving at incredible speeds.
So it's like trying to tame a wild stallion.
Yeah. Yeah.
You need the right tools and techniques
It is.
to harness its energy and make it work for you.
You got it.
So what are some of the strategies they're using?
Well, they're getting pretty creative.
Okay.
One approach is what they call trimming the magnetic field. It's like shaping a magnetic field. Like you're pruning a bonsai tree, trying to achieve that perfect form.
I love that analogy.
Yeah.
It makes it so much easier to visualize.
But keep those frequencies stable.
So they're essentially fine-tuning the magnetic field
Exactly.
to keep those magnetrons in check.
You got it.
What else?
Another key strategy is leveraging commercially available components.
Okay.
This helps keep costs down.
Right.
And makes the technology more accessible.
That makes sense.
They're also developing smart controllers.
Smart controllers.
Yeah.
Okay, break that down for me.
Sure.
What are smart controllers?
So they use something called field programmable gate arrays.
Field programmable gate arrays.
Yeah. Think of them as tiny, customizable computer chips that can be programmed to perform specific tasks.
So they're giving them a brain boost.
Yeah, basically.
To make them more reliable and controllable.
Exactly.
Pretty ingenious.
Yeah.
And they're not just going at it alone, are they?
You got it.
Science thrives on collaboration.
Of course.
So who are they working with?
Jefferson Lab is partnering with several companies and universities.
Teamwork makes the dream work.
Exactly.
Right.
It does.
What kind of expertise are they bringing in from the outside?
So they're working with companies like Muons Incorporated.
Muons Incorporated.
Which is an accelerator physics company from Illinois.
Okay.
And InnoSys Incorporated, a manufacturer of smart power supply controllers from Utah.
So they've got the brains and the brawn covered.
They do.
It sounds like a real dream team.
Yeah.
What about the universities?
While the article doesn't specify the university is involved, it's likely they're contributing expertise in areas like materials, science, electrical engineering, and physics.
You need a diverse set of skills to make a project like this successful.
Absolutely.
I remember our source mentioned something about using specific frequencies for these magnetron-powered accelerators.
Yes.
Can you shed some light on that?
Sure. They're focusing primarily on frequencies of 915 megahertz and 2.45 gigahertz.
Okay.
You might recognize these from your microwave oven or other common devices.
So using these readily available frequencies means that they can utilize off-the-shelf components.
Exactly.
Which, again, is a clever way to keep costs down.
You got it.
That's smart.
Yeah.
So is there a scientific reason for choosing those specific frequencies?
It's both, actually.
Okay.
Those frequencies happen to fall within a range that's suitable for the types of compact accelerators they're developing.
So they're hitting that sweet spot where practicality and scientific requirements align.
Exactly.
I also remember something called a magic T being mentioned.
Yes, the magic T.
What is that?
It sounds like something straight out of a fantasy novel.
It does.
But it's actually a cleverly designed piece of engineering.
Okay.
It's a type of waveguide junction.
A waveguide?
Yeah, think of it like a pipe.
Okay.
But for electromagnetic waves instead of water.
Okay.
It's designed to guide those waves. Like microwaves, along a specific path.
Okay.
And a junction is simply a point where multiple waveguides come together.
So the magic T is a way to bring together multiple waveguides.
Yes.
Why would you want to do that?
It allows you to combine the power from multiple magnetrons. Think of it like this.
Okay.
One horse can pull a cart.
Yeah.
But 4 horses working together can pull a much heavier load.
It's all about boosting their power output.
You got it.
And I remember they talked about power combining too.
Yes.
Is that the same thing as the magic T?
You're picking up on the nuances.
Oh, am I?
Power combining is the overall strategy of combining the output of multiple power sources.
Got it.
The magic T is just one specific method they're using to achieve this with the magnetrons.
So the magic T is like a tool in their power combining toolbox.
Exactly.
That makes sense.
It does.
What about those smart controllers?
Oh, yeah. Those are crucial.
Yeah.
For ensuring that the whole system operates smoothly, think of them as the conductors of an orchestra. Making sure all the instruments are playing in harmony.
Right.
They're constantly monitoring and adjusting the magnetron's output.
Yeah.
Ensuring stability and precision.
So it's all about maintaining that delicate balance.
You got it.
Right.
Too much power and things could go haywire.
Right.
But too little and you won't get the desired results.
All this talk about precision and control reminds me of something we touched on earlier.
Yeah.
Those klystrons are known for their precise control.
They are.
Over particle beams.
Yeah.
But are magnetrons catching up in terms of precision?
That's the million-dollar question,
Yeah.
and it's precisely what researchers are trying to figure out.
Could they potentially offer the best of both worlds?
That's the hope.
High efficiency and precise control.
If they can successfully combine the efficiency of magnetrons
Yep.
with the precision of klystrons,
Right.
it would be a game changer.
Like having your cake and eating it, too.
Exactly.
So let's imagine for a moment that they crack the code.
Okay.
What would that mean for the future of particle physics? What kind of impact could we see?
I mean, imagine shrinking those massive particle accelerators
Oh, yeah.
down to a size that could fit in a hospital or even a lab on wheels.
That would be wild.
It would.
What if cancer treatment could be delivered with a device the size of a microwave?
It's the kind of future this research could unlock.
That's incredible.
And what if we could analyze materials at the atomic level, right there on the factory floor?
It would democratize access
It would.
to this cutting-edge technology.
Totally.
And the implications for scientific discovery.
Oh, yeah.
I mean, could we unlock new mysteries
For sure.
of the universe
Oh, absolutely.
if we had smaller,
Yeah.
more portable, more affordable particle accelerators?
Well, sure. And,
Yeah.
our source specifically mentions
Okay.
that Jefferson Lab
Uh-huh.
is even exploring the possibility
Okay.
of using magnetrons
Yeah.
to power their CBAF
The
accelerators.
CBAF accelerator.
One of the most advanced research facilities in the world.
So they're thinking big.
They are.
If they can pull that off,
I know.
it would validate this whole approach.
It would send shockwaves
Yeah.
through the scientific community.
And think about the cost savings.
Oh, yeah, huge.
I mean,
It's millions.
Our source estimates that switching to magnetrons could save Jefferson Lab millions of dollars each year
At least.
in energy costs alone.
Yeah.
That's wild.
Especially in a time when research funding is so tight.
Right.
It could free up resources for other important scientific endeavors.
Yeah, absolutely.
Yeah.
But let's zoom out for a second.
Okay.
This research,
Yeah.
it isn't just about magnetrons and particle accelerators.
No, you're right.
I mean, it's about so much more than that.
It is.
It's a testament to human ingenuity.
Yeah, absolutely.
Our ability to find solutions
Right.
to complex problems.
To overcome these challenges.
It also highlights
Yeah.
the importance of collaboration,
Oh, for sure.
bringing together experts from all these different fields
Yeah.
to push the boundaries of what's possible.
Absolutely.
Sometimes the most groundbreaking discoveries come from looking at familiar things with fresh eyes.
I think that's a great point.
Who would have thought
I know.
that the humble magnetron,
Right.
that thing we use to reheat our leftovers,
Yeah.
could hold the key to revolutionizing particle physics?
It really makes you wonder.
It does.
What other everyday technologies
Right.
might be hiding extraordinary potential?
What else are we taking for granted?
I know.
That could be the next big scientific breakthrough.
It's a question we should all be asking.
It is.
Yeah.
It's a call to action.
It is.
To be more curious,
Yeah.
to be more observant,
Yeah.
and more willing to challenge conventional thinking.
Absolutely.
You don't need a fancy lab or a PhD to make a difference.
Right.
Sometimes
Yeah.
the most important discoveries
Mm-hmm.
start with simple questions
Right.
and a healthy dose of curiosity.
Exactly.
So what's the one key takeaway?
I think the biggest lesson
Yeah,
is that innovation can come from the most unexpected places.
that's true.
Don't underestimate the power of everyday technology
Right.
or the importance of collaboration. The next big breakthrough
Yeah,
could be hiding in plain sight,
absolutely.
just waiting for someone to ask the right questions.
To all our listeners out there,
Yeah.
keep exploring.
Fantastic.
Keep questioning and never stop being curious about the world around you.
The world is fascinating.
You might just stumble upon the next scientific revolution.
You never know.
And until next time,
Yes.
keep diving deep.